Okay, so we're back. Hopefully you were able to successfully complete the workshop. And for this one, instead of building it from scratch, I'm just going to go through the solution object by object. And so we have the part arrival process inter-arrival times uniformly distributed between 0.75 and 1.25, and so that's fairly straightforward. We just specify the inter-arrival time distribution here, and we also specify that the entity type is parts. We have pallets, and again, pallets are determining the number of pallets is a decision variable. So we're going to create pallets. The number that we're going to create, we will use a reference property. So we defined a reference property for the entities per arrival, and we specified the maximum number of arrivals to be 1. So at time 0, we're going to create the number specified by this reference property of pallets, and we won't create any more, and so they recirculate around the system. The palletizer and depalletizer processing times. So the combiner models the palletizer, and so we have the random uniform 10, 20. Remember also that this is in seconds, where some of the other times are given in units of minutes. And for the separator, we have the processing time is specified the same way. All of the other parameters, our property values for the separator, are left at their default values because we're splitting batch members that were created in the combiner. The pallet return is 15 minutes, so we used a time path for that. So there's the time path. The part processing time, which I somehow skipped, we have for each part is exponentially distributed with a mean of 0.9. So for this sample, we use the math.sum of samples, and so let me extend this so we can see it. And so we just have that pallet capacity as a reference property. So we have two reference properties. If we jump over to our definitions and go to properties, we have two reference properties, as I said, the number of pallets and the pallet capacity. And so when we look at our model parameters, our model properties, we can see those two controls right here. And so for the interactive run, we're creating 10 pallets. Each pallet has a pallet capacity of 4. And so when parts come out of the separator, they leave, and when pallets come out, they recirculate around. So the basic structure of the model is set. So now we need to incorporate our system cost and profit, and so to get our total profit. And so if we have a system cost of number of pallets times the pallet capacity times 100, which was the pallet cost for each pallet type, and then we need to count our earnings for each part we created. So what I did was created an output statistic that took the number of parts that came through the sink times 1 for my profit minus the system cost. And so if we go to definitions, elements, I created an output statistic called total profit by simply putting that expression and setting the unit type to currency. And so that creates an output statistic for each run that will give me the total profit. Okay, so if we go to the experiment now, we need to see how we incorporate our requirements. So here's the experiment, and so we see that the default experiment has the controls set up as the two reference properties, the number of pallets and pallet capacity. And the responses that we created were the time in system. So this is just the sink.time in system average. So the average time that the parts that go through the sink spend in the system. We have the profit. In this case, I'm using profit as the total profit dot value. So this is the output statistic. Note I mentioned in the hints that this was an optional to have an output statistic. I could also have just created an experimental response and then just put the expression right here. So rather than create an output statistic, I could have just put the expression right here and we would still see that profit show up. We also have throughput because we have a throughput constraint, and so the throughput would simply be the total number of parts that were created divided by the current time. So time now computed or expressed at the end of the replication would simply be the total runtime. And so for the throughput and the time and system, we have constraints. And so if you look at the throughput, I put a lower bound at 55. And for time and system, I put an upper bound of 1. Make sure that time unit is in hours. We also threw in the number in system just so we could keep track of the number of parts in the system at any time. And so also note that in the experiment, because we're trying to optimize the system, in other words, trying to determine the number of pallets and the pallet capacity, we just enumerated several different alternatives. So we know that we have options for pallet capacity of 2, 4, and 6. And so we created experimental scenarios with 1 pallet, 2 pallets, 3 pallets, 4 pallets, and so on up through 11 pallets. And finally, one thing that I forgot to mention that if we look in the if you back up in the video, you'll see this is I forgot to set the ending type. If you remember back from our problem definition, it said we wanted to run for 100 hours. And so I have to set that by going for ending type and setting a fixed run length to 100 hours. And so previously in the video, I just hadn't set that. So if you look backwards, you'll see the sort of the default of 24-hour run. So I went and set it. And now that we can go back, we can actually run our scenarios. So if I click run, we're going to see it start running. And one quick thing, let me cancel this and talk about this because it comes up. You're going to see this warning here. So warning from scenario 6, replication 1 at time 94. The maximum number in system for parts has been exceeded. So if I could look at scenario 6, this is a 2 pallet 6 capacity. And so what's likely happening here is that we don't have enough capacity to handle the arriving parts. In other words, we don't have enough pallets so that parts don't keep piling up. And so what I'm going to do is just let this run because it's just a warning. It's not an error yet, and so we're just going to let that run. And so I'm going to then go back and continue running my experiment, and then we'll come back in the video when the experiment finishes. Okay, so we're back, and you can see that it took 109.3 seconds on my computer to run all of those scenarios. And you can see some of the values are shaded red. Well, the values that are shaded red mean that they don't meet the constraint. So we have a constraint on time and system of 1 hour, the lower bound of an hour. So anything that doesn't meet that constraint is shaded red. Similarly, for the throughput, we have a minimum constraint of 55 that we set here for the lower bound. And so anything that doesn't meet that constraint is also shaded red. Profit is what we're trying to optimize. So what I would do now is I would go and sort in descending order to give me the highest profit values first. And then we would simply pick the first scenario that meets both of the constraints. And so that would be, in this case, scenario 31, which is 11 pallets with pallet capacity 2. Now note that the capacity, the number of pallets 11 is the maximum that I experimented with. So if I were really trying to solve this problem, I would likely go back and add some additional scenarios with more pallets, because it seems like what this system is favoring is a large number of pallets with a small capacity. But that's something that you should experiment with with some further experimentation. Note also that this would be an excellent opportunity to use the Simio add-in OptQuest, which is an optimization package specifically designed for problems like this, where you're trying to optimize a value, a cost value, by manipulating values of decision variables. We'll see that later in the course, but just keep in mind that this would be a great application for that add-in. And the last thing I want to go back and revisit is this notion of the warnings we were getting. We were exceeding the maximum number of entities. So if we go back to the model and go to the part entity and jump to the population, we can see that this maximum number of 2,500 is default, the default value set by Simio, but I can change that. So if I wanted to make sure that I don't actually have an error in my model that's causing this warning, I could just set this value to a bigger number. So you think about how big should I set it? Well, if we look at how our inner arrival time, so our inner arrival time is approximately, or on average, 1 minute. So that would say that on average we're going to have 60 parts arrive per hour. We're running for 100 hours, so the maximum parts that we create are 6,000. So I could just go in here and set this to 6,000 right there, so that maximum number, and then I would go back in my experiment, reset, and run, and that warning should go away because we shouldn't ever exceed that 6,000 because that's the maximum number that we create. So again, this is something that you should experiment with because that warning is there in place because the building up of entities is often indicative of a logic error in your model where you're not appropriately destroying entities or they're not going to a sink, and so that's why that warning is in place. In this case, it's simply a capacity problem, and so you would see when you run this that that does in fact solve the problem. And the last thing that we didn't cover in the workshop in the sample in the explanation that I gave is the animation component. And so for the palettes, what we did was we used a palette symbol and then we used the batch queue. So we used the batch queue to make it look like the parts were on the palettes. And so this is exactly what we demonstrated in the previous video. And so that's definitely something you should also give a try to. And so that completes this workshop. If you struggled at all, I would highly suggest that you go back and review, maybe watch the video again, or maybe try to build the model again. There were some very important points covered in this workshop, and as I mentioned at the start, this is the first workshop that we've done where we're actually solving a decision problem. We're not just building a sample model, but we're actually building a model that we're using to solve a problem, to answer a decision problem, which is typically what you're going to want to do with simulation going forward. So that's it's important that we have a good understanding of those basic concepts.